For our project, we chose to optimize the design of a basic playground swing set. The goal of the project was to blend the constraints and forces of the existing structure into the optimized design in order to use less material while still properly supporting the swingers. The current design uses 6 leg supports and 1 top bar and is most commonly made of drawn steel. For simplicity, we divided our project into 2 optimizations. The original leg design uses 3 bars constrained at the bottom and subjected to 3 forces at the top. For symmetry purposes, only 1 unit needs to be analyzed. The original design was modeled as a frame system made of beam elements. The system has a maximum stress under 600 psi and a maximum displacement under 1/10 of an inch. We applied our boundary conditions into topology optimization, and after 2 iterations, a final wishbone design was selected. The wishbone design was then subjected to the same ANSYS analysis. This analysis showed comparable results to the original design.
First, we analyzed the original beam as a beam 120 inches long with a diameter of 2.4 inches, with the forces and boundary conditions as shown. We analyzed the beam in ANSYS using 3D tetrahedral elements. Later, we're going to compare the results from this analysis to our final designs. One of the biggest issues of optimizing this beam is that it has a very big aspect ratio since the diameter of the beam is so much smaller than its length. So we have issues of finding the right resolution and number of elements so that we can use the topology optimization. We downloaded software that allows us to change the number of elements used in the X and Y and Z directions. We ran the topology optimization using a reduced aspect ratio with the intent of scaling it up later on. In the results here, we actually have a 3D object that we can model using 3D tetrahedral elements, as opposed to the previous case of legs where we ended up analyzing the structure using beam elements. One of the issues with the structure that we have here is that the force applied on the beam is not constant. It is not down. And that kids actually swing when they sit on a swing. We had to get creative in order to solve this, so we took a cross-section of this structure right at the center, and we cut that cross-section in half, and we revolved it 360 degrees. The result is this structure here. The problem with this structure is that it has an aspect ratio of 10 by 10 by 42. Obviously doesn't match the original beam. So what we did is we scaled the original cross-section that we came up with, and we again cut it in half and revolved it around so that we have now a beam that is closer to 4 by 4 by 120. When we took this cross-section and loaded it into ANSYS, we found that the geometry was problematic. There was too much detail and there were too many points. We simplified the geometry, arriving at iteration number 2, and we loaded that into ANSYS. And this simplified geometry worked much better. In order to be able to see the results on the interior of the beam was cut in half and a symmetry boundary condition was applied on the cut face. The results of stress and displacement are good, but since we didn't match the diameters of this design and the original beam, the volume is 40% larger. For the final iteration of the design, we further scaled down the diameter so that its max is equal to the original diameter. Furthermore, rather than cutting the cross-section in half, we kept both the upper half and lower half of the cross-section. We revolved each half 90 degrees both ways so that they met at the center. Finally, in order to further reduce the sharp points and edges, we extruded a small diameter through the center of the beam. The same loads and boundary conditions were applied in ANSYS. The maximum displacement of this optimized beam is higher, but that's expected because all we did was take the original beam and remove material from the inside and the outside. The maximum stress is also significantly higher, but we find that this only occurs at the ends where the diameter is smaller, and it doesn't occur at the center where the beam has a thin wall. So we find that it's not too concerning because this can be resolved by increasing the diameter or changing the boundary conditions there. We compared the maximum stress, maximum displacement, and volume of the designs. We found that the final design reduces the volume by 35%.